Hello all, welcome to video 2 for section 4.6, all about rank. So yeah, we mentioned the word rank, but didn't say what it meant. So now let's go ahead and do that. As soon as I find the piece of paper that I'm going to find. Page 5. Here we go. Right, so the rank of a matrix A is the dimension of the column space. And the very first thing we're going to say about it is this. The dimension of the column space and the dimension of the row space of an n by n matrix are equal, in fact. And moreover, the rank is equal to the number of pivot positions in A, and so it satisfies this nice equation that the rank of A plus the dimension of the null space of A is equal to n. And we can give a rough idea for both of these statements. So what? We know that the dimension of the column space of A, which is the rank, is equal to the number of pivot columns. Oops. Pivot columns. But each pivot column gives you a row with a pivot in it. We call them pivot rows. But the pivot rows are exactly the non-zero rows in the echelon form. So that's giving you the dimension of the row space of A. Okay, so there's our first statement. The dimension of the column space and the dimension of the row space of a matrix are equal. And then finally, why is it the case that these things sum up to n? Well, we know that each pivot, what do we know? Each variable is either free or non-free. Every free variable contributes to the dimension of the null space. And every non-free variable contributes actually to a pivot position. And so, the total number of variables is n. They're either non-free or free, so the two of those things together must sum up to n. Okay. Oh yeah, and then so we've got n variables. Oh. Each free one contributes to the dimension of the null space. Each non-free, contributes to dimension of the row space of A, which we know is equal to the dimension of the column space of A, which is the rank. Okay. Let's look at some examples. So if A is a 5x7 matrix with a 3-dimensional null space, we might want to know what the rank of A is. And okay, A is m by n, so the n that we care about is 7 here, and so our rank theorem says what? It says that 7 is equal to the rank of A plus the dimension of the null space. We're looking for the rank of A. We know the dimension of the null space is 3. Okay, so then the rank of A is 4. Not so bad. More examples. Could a 4x8 matrix A have a 3-dimensional null space? That's a little harder, but still manageable. So A has 4 rows because it's 4x8. L for linear algebra, 4x8. So it has 4 pivot positions. Has at most 4 pivot positions. And so that means that it has at most 4 pivot columns. So the dimension of the column space, or the rank, has at most 4 vectors in it. So our dimension of the column space of A is at most 4. Okay, and what we're going to do, now that we've sort of figured out how these bounds impact the rank, is we're just going to go back to this very friendly equation impose the bound on rank and see how that impacts our possible null spaces. Okay, so again, our rank theorem says that 8 is equal to the dimension of the column space of A plus the dimension of the null space of A. And we know at most this is 4. So 8 is actually less than 4 plus the dimension of the null space of A. And what this means is we can still subtract 4 from both sides of an inequality, and saying the dimension of the null space actually has to be at least 4. So can it be 3-dimensional? Absolutely not. This is saying the very smallest it can be is 4, and the smaller the dimension of the column space is, the bigger the dimension of the null space has to be to compensate. Right, so no. Dimension of the null space can't be 3-dimensional. Okay. What else do we have for you? Here we go. Suppose a homogeneous system AX is equal to 0, 5 equations and 6 variables, has solutions that are all multiples of a single vector. Does the non-homogeneous system AX is equal to B always have a solution regardless of the vector B? Seems like a completely impenetrable problem until you realize actually it's not so bad. It's all of math, by the way. It seems impossible until something makes sense and it's not so impossible. Okay, so let's try and pick at all the relevant information. 5 equations in 6 unknowns is a 5x6 matrix. A is a 5x6 matrix. The homogeneous system has solutions that are all multiples of a single vector. That means that the dimension of the null space is 1-dimensional. It's a single basis vector. Multiples of it are yeah. So we know dim null A is 1, since all solutions of the homogeneous equation are multiples of a single vector. Okay, so now we've got a 5x6 matrix. We've got that the dimension of the null space is 1. This is already going to give us some information about the rank, and then we've got to figure out how that rank helps us. So again, our rank theorem says what? Says that 6 is equal to the rank of A plus the dimension of the null space of A. So 6 is equal to this rank plus 1. Okay, so we're getting the rank of A is equal to 5. Now we need to stare at this for a second, figure out how is this helpful. So the rank we can think of as the dimension of the column space. We can think of it as the dimension of the row space. Same thing. And this time I think row is going to help us. This is saying each of the 5 rows of A contains a pivot. Each of the 5 rows of A contains a pivot. And now something clicks on from like week 2, where we had a theorem that said if every row of your matrix contains a pivot, then the columns span Rm or Rn. Has to be Rm. Yeah, so then by theorem 1.4, yeah, the columns of A. I mean, sorry, we don't need to go the columns of A span, but by theorem, by the exact same theorem, we know that for every, yeah, that AX is equal to B is consistent for every B. pivot. So by the theorem 1.4, AX is equal to B is always consistent. Boom. So then it doesn't matter. Yeah, that answers the question. The non-homogeneous system always has an equation. Yeah, for sure. And so the non-homogeneous equation always has a solution. Okay. And then the last thing I wanted to add was, yeah, some in addition to our very long invertible matrix theorem from chapter 2. So yeah, we can add the following to our IMT. I'll let A be an n by n matrix. A is invertible if and only if any one of the following holds. So we had A through L before. So we've started at M, obviously. So right. So what else is the same? So the columns of A form a basis of Rn. Yeah, which is clearly equivalent to the column space being Rn, or the dimension of the column space being n, or the rank being n, or by the rank theorem, that means that the null space has to be just the 0 vector, or the dimension of the null space is in fact 0 as well. And there's a quick proof in the textbook. I'll save it for you to look up. Okay, yeah, take care everybody. I'll see you next time.